we want to take some time to talk about what we're going to cover in this program. This is going to be evaporative emission control systems, and we're going to try to make this a composite from early to modern, latest vintage systems. We want to provide you with keys to productive Evap diagnostics because Evap diagnostics are frequently a cause of problems. We want you to develop an understanding of Evap strategies for most of the OBD1 and OBD2 vehicles. We say most because we have never seen anything that's 100% complete. We've tried to make this as complete as possible. We're going to give you different information for domestic and import light-duty vehicles. We're going to give you a thorough knowledge of the different strategies. We're going to talk about some of those strategies. Evap trouble codes will be later included one by one, and we're going to show you step by step how to go about diagnosing the most common SAE trouble codes on vehicles. Now, here's an idea for you to understand. We talk about variations. There's 9 different enhanced systems covered in OBD2. These are 2000 and later. We have 9 different vehicles. Not 9 different vehicles. There are 9 different Evap system strategies for detecting leaks. Not all work the same way, and you should develop an understanding because sometimes it's the appliance we put on to do the leak testing causing the problem, and you make it easier to find. We want you to use aftermarket equipment for efficient diagnostics. We say aftermarket because all too often we look at the instructions in the service manual. They're asking you to use some specialized piece of equipment. Push button A, does it read 10? Yes or no? Well, if you don't have that specialized piece of equipment, that's useless. We're going to be using scan tools with bidirectional control. Yes, that means you're going to have an enhanced scan tool that can give you bidirectional control. And we're going to be testing with digital multimeters and, of course, smoke machines. When it comes to 20,000 leaks, there's no other machine that's going to work. It's hard enough to find them with a smoke machine. Without one, it's impossible to find a 20,000 leak. And we're going to be using not just smoke, but we're going to be using a smoke machine with a flow meter. We're going to check for restrictions, measure the leaks so we can measure improvements, and then use smoke to pinpoint the problem. Smoke is not everything. And we like those smoke machines that have a dye in case you can't see the smoke, but we can localize an area. We can go back with a UV and see with a dye where it's leaking. Now, think safety for a minute. This is something we have to say. Be careful when using shop air for Evap testing. Adding air to the fuel tank creates a highly combustible mixture. Let's define combustible. Combustible means you have air, you have fuel, and you only need a spark for combustion. Flammable means you've got a fuel. You give it air, you give it a spark, then you can have a fire. We're beyond flammable. So most vehicle manufacturers recommend the use of nitrogen or CO2 as a purge gas. Now that is much safer because neither one will create a combustible mixture. Remember, you're pumping this stuff out. You're pumping out hydrocarbons that's combustible. Do not perform these tests near an open source of flame or spark. And remember, fires can be caused by arcing wires and connectors on the vehicle. And for God's sake, don't use with open heaters in the shop like a torpedo heater in the wintertime because you've got the shop closed up and you can have a fire. Go on the internet, see how many fires are caused by Evap systems putting out so much vapor it catches things on fire. Let's go back in Evap history for a minute. In 1973, the EPA issued rules that evaporating fuel vapors had to be absorbed by a charcoal canister and then recycled into the intake manifold. And this system is simple. Manifold vacuum pulls fresh air through the canister, and we're going to talk about all these parts and pieces when we start getting ready for trouble codes. But let's talk more about what we've got here that people forget about. We have a liquid separator, which prevents liquid from going into the canister and flooding the canister with liquid. It deteriorates the charcoal and causes extremely rich mixture when we purge. This was also called a rollover valve in the early days. Sometimes these become defective and you'll have very rich mixtures. And you won't set a code because of it, but you'll have trouble getting Evap to run. As the manifold pulls this fresh air through the canister, it sucks in all this fuel, and you can get some real bad contamination of the purge solenoid from that. Now, after the introduction in 1973, evaporative emission systems have undergone numerous changes. Early systems had limited diagnostics, like OBD1, usually dealing with electrical operation solenoid and switching valves, and some vehicles had vacuum sensing switches to self-wet a vacuum. Now, we're going to develop a diagnostic that can be applied from early systems to late systems. Most of the time, we're looking for leaks. The question is, how big is the leak? That's what changes. The evolution of OBD2 enhanced evaporative emissions has complicated the Evap system because they have improved leak detection. We can find leaks with OBD2 we could not find with OBD1. In 1996, the start of mandated OBD2 up till 1999, we had to find a 40,000th leak. Now, don't think this was chiseled in stone. Some vehicles were granted waivers initially because they couldn't meet this. They had to meet it later. 2000 and later, the enhanced systems had to improve to identify leaks as small as 20 thousandths of an inch. That 20 thousandth of an inch detection has increased the frequency of diagnostic trouble codes for leaks. And why is the only reason we're working on this system? Probably because it's got a trouble code. A 20,000 leak are more difficult to locate in many cases, particularly if they're located in some inaccessible place like the top of the fuel tank, wherever it might be. Let me tell you how small 20 thousandths is. 4 pinhole-sized leaks, the size of an average human hair, can be detected by the 20,000th leak check. If you happen to be unlucky enough to have a vehicle that does have 4 pinholes, you better have a diagnostic procedure that can help you find enough to get it down below 20 thousandths. Will 1 pinhole do it? Good question. Will 2? Probably, but you need to measure that. We're going to talk about that. Some repairs become difficult when the leak is caused by these several small things. You need to verify the repair and correct all of the issues before returning the vehicle to the service. We're going to talk more about that. But they require detailed understanding of how the different Evap systems work and what you're going to be seeing. We're going to use the diagnostic procedures that's going to fit most of them. And we're going to focus and give you specific step-by-step for the diagnostic trouble codes. We're going to use testing approaches that's sufficient enough to allow you to do before and after testing. Test it before, make a repair, measure the improvement, and talk about it. And know that you're going to pass the test. Because remember, some of these vehicles won't run a test very easily unless you happen to be lucky enough that has one that'll run the test in the service bay. But even then, with a 20,000th leak, you're not going to get to run until the next time it runs the monitor. And that may require a lot of time. When we get to those various systems, that's what's different about those 9 different systems. How do they find this 20,000th leak? Now, statistics don't fix cars, but the SAE did a study in 1990 with the enhanced OBD2 and found out here's the problems they have. We have a lot of people that says, well, my strategy is to change the filler cap, gas cap, whatever you want to call it, and see if it fixes the problem. Well, that's going to fix it about 23% of the time. That means 77% of the time, it won't fix it. Let's say that again. If we're using statistics, that says that 77% of the time, you're not going to fix the car by changing the gas cap. And how are you going to know you didn't fix it? You're going to give it back to the customer and have them come back later? If you want to go statistics-wise, change the hoses. They fix about 30% of the problems. There'll be a lot of time involved. And again, 70% of the time, you're going to be wrong. So I hate people say, well, when I had a 20,000th leak, I changed this component. That means nothing. Here's a list of things that fix 20,000th leaks. Recently looked up an internet site. We had a problem on a car, and it said we changed this solenoid, this sensor to fix a leak. And we went, wow, but we have a leaking. We smell the smoke. We smell the fuel. We know we have a leak that's not one of these sensors. So don't buy these things that says change a bunch of parts, see if it fixes it. That's a very expensive way to fix Evap. It's expensive enough for the labor-intensive issue of diagnostics. That's where our issue is. OBD2 diagnostics could not detect leaks like a filler cap. So if you're working on one, don't think that. If you are an enhanced system, a good diagnostic starting point for enhanced systems would be to check the filler cap early in the diagnostics. Just remember, It will not correct the old OBD2 problems. It's never, 100% of the time, going to be fixed by a gas cap. They can be either tested with a tester or replaced. But if you replace it, what are you going to test it? How are you going to verify that replacement did something? Like we said, 23% of the failures are filler caps. It's easy to check, and we can replace it. But if you replace it, if you want to try the replacement, the system must be checked for flow before and after and measure any improvement. You may have one of those that has 4 little pinhole leaks the size of a human hair, and maybe one of them is a gas cap. If we check the flow restriction before and the flow restriction after when we seal the system, then it'll tell us if we've made an improvement. If we've made an improvement, keep the gas cap. If you didn't, you haven't done anything. Okay, so we want to have a procedure for checking and measuring results. That's important. Evap codes are a frequent reason for a comeback after repair. In fact, in some cases, if you look at it on the number of repairs done for Evap and the number of comebacks, it has a very, very high comeback ratio. You have equipment for gas cap testing if you want to test it. This is an inexpensive system. There's a more elaborate system made by Wacom that's even more sophisticated than this, but one of them, either one will work, or replace it will work if you have something. We're going to be using codes. Remember, diagnostic codes, we say politically correct, is the frequent reason for checking Evap. Let's be honest, the only reason you're going to be working on Evap is because you have a code. No customer is going to come in and say, hey, I need to get my Evap checked. I've got 60,000 miles and I don't know how well it's doing. Customers care less. They only care about that check engine light. And codes can be used to point us toward the problem area as a likely cause of the problem. We're going to spend time talking about this. Some codes point us to an electrical area. Some codes point us to a flow area. Let's see which one it is and talk about those. We're going to give you examples of OBD1 and OBD2 codes, and we're going to give you a complete list of codes. We're going to start off by what would we do if our P0440. That takes us back to OBD1, where we had a system that says no flow was detected, or to enhance, which says it failed to pull a vacuum. Talk about the differences and see the differences in strategy. This changes with different generations. So we're going to be doing all that, and after we get through our initial study of the Evap system and all the components of the Evap system, we're going to go in and go through specific codes and give you step by step for each code. So let's go now and have a look at the sample codes, understand the operation of all the parts we're going to be testing.